Hey, hello, everyone. I'm Alex Gough. I'm a PhD student at Newcastle University, and today I'm going to tell you about how a simple wave model of dark matter can encode multi-streaming information in wave interference. The paper on this project has just gone up on arXiv, so if you're interested, I hope you'll have a look and come and find me to chat later at some point during the conference. At a high level, I work on cosmic structure formation. From measurements of the cosmic microwave background, we know that the early universe is extremely uniform, with typical variations in density being only about 10 parts per million. This is in stark contrast to what we see in the late universe, where the matter is distributed into much more complex structures with dense filaments, sheets, and knots, and huge underdense voids. By mapping all the galaxies in the sky with telescopes, we can see this cosmic web with structure on all scales. The big question in structure formation is then, how do these tiny initial seeds of structure from the early universe evolve to become this complex network-like structure? We know today that the key ingredient for this evolution is the dark matter component of the universe. Since there is about 5 times more dark matter than ordinary matter in the universe, the gravitational collapse of the dark matter dominates the history of structure evolution. This builds a kind of skeleton on which the galaxies and baryonic matter then trace to give us the cosmic web. In the standard cosmological model, the dark matter component is a collisionless, non-relativistic dark matter, which we call cold dark matter. We'll mostly be talking about a different viewpoint today, where the dark matter is treated as a single wave function, which we'll call wave dark matter. So the panel on the left here shows the result of a cosmological simulation with cold dark matter particles, and we can see this web-like structure that connects the collapsed structures. On the right, you see the result of a wave dark matter simulation, which you can see produces the same set of large-scale features, but on small scales, the wave dark matter sort of decorates this cold dark matter skeleton in interference effects. So if we looked at a one-dimensional slice of this system, you might see something like the following. The black line here shows the cold dark matter density with 2 highly dense peaks, which would be the collapsed structures. And the blue line shows how the wave dark matter follows this classical density profile, but it provides additional interference features that give you extra details. So why might we want to treat dark matter as a wave? Well, certain models of dark matter have this wave-like behavior as fundamental. It's a true quantum waviness described by their quantum wave function. This is only relevant in astrophysics or cosmology if the de Broglie wavelength is sufficiently large, but there are particular dark matter candidates such as ultralight axions that do satisfy this criteria. The other view, and the one that I'll focus on today, is that we can use a wave function model of dark matter to overcome certain difficulties in modeling cold dark matter. And then we can relate the results for the wave dark matter to the cold dark matter via a sort of correspondence principle, in the same way that you can relate quantum systems to classical systems in a semi-classical limit. So if we're going to use a wave model to understand classical dynamics, let's first discuss what the phenomenology we want to capture in this classical dynamics is. So we'll do this by looking at a very simple model that captures the features of interest, which also occur in the fully nonlinear case. So if you put a dark matter particle into some initial gravitational potential, how does it move in response to that potential? Well, at least at the start, it's given a velocity which is just the gradient of that potential. So an approximate solution for the motion of these particles is just to shoot them at this initial velocity and let them travel in straight lines. Doing this, they end up at final position x, which is related to their initial position q, just by this constant velocity. This approximation is called the Zel'dovich approximation. And while this model is very simple, it's extremely useful and performs very well on large scales. There are some obvious problems with this model, namely that since we don't update the particle velocities, there's no way to get them to turn around once they've passed through each other. The natural extension to this approximation is called Lagrangian perturbation theory, and it encodes both this Zel'dovich approximation and tidal effects. However, we're going to be focusing on a one-dimensional model where the Zel'dovich approximation is actually exact before the particle streams begin to cross through each other, which we're about to see. Here I have a video showing both a set of cold dark matter particles and the density of the system as a function of time. And everything will be evolving according to the Zel'dovich approximation. As time moves forward, the density in the center builds up and up, until it diverges to infinity at an event called shell crossing. After this happens, different streams of dark matter flow through each other because they've been mapped to the same final position, even though they started at different initial positions. So after shell crossing, these particles continue to flow through each other, and we have two walls of infinite density moving apart from each other. We can have another look at this system. Now we're looking at the density in the top plot, and on the bottom we show the phase space sheet, which shows the velocity as a function of position. Our initial conditions are just that we start with a uniform density of particles and a sinusoid in their velocities. So we're essentially studying just a Fourier mode. So we can begin this again, and as the density builds up in the center, the phase space sheet begins to twist, and at shell crossing, the center of the phase space sheet becomes vertical. After shell crossing, the phase space sheet becomes multi-valued, representing the multiple velocities at a single position. This is the phenomenon of multi-streaming in cold dark matter. We now want to compress all of that information we just learned into a set of figures that we can look at. So the first way we can do this is by plotting the full phase space sheet over time. We see the initial sinusoid twists over itself in time to produce multiple streams. If we project this sheet down onto the space-time diagram, we get something like the following, where individual threads in this weaving show individual particle trajectories. In the outside region, we have a single stream, just a single trajectory going through each point. But there's this region in the center, corresponding to the multi-stream region, where we have 3 particles going through each point. There's a sharp boundary between these 2 regions, which, remember, corresponds to the formerly infinite density spikes we saw, and this is called the Caustic line. This problem of multi-streaming shows us one of the key challenges in modeling cold dark matter, because we can't just use a perfect fluid to describe the dynamics of this system, because a perfect fluid has single-valued density and velocity. So to recap, we have cold dark matter, which deals with collisionless particles, and we have wave dark matter, which deals with wave functions. We've seen that the very simple Zel'dovich approximation includes some of the complex phenomena that we want to understand, which is multi-streaming. So what's the corresponding simple model for the wave dark matter case? Well, perhaps not too surprisingly, the simple model, which we've just described in the wave case, is just the free Schrodinger equation, where our wave function, which describes our dark matter field, evolves with time according to this equation. Now notice here that we've introduced h bar, which will act as a parameter in our theory. So the limit of h bar going to 0 should push us towards classical mechanics. So how should we go about building the wave analog to what we've just looked at in Zel'dovich approximation? Well, if we write the wave function in polar form, we can recover the density from its amplitude, and the velocity simply is the gradient of the wave function phase. So to build the analog system, we need an initial wave function with a uniform density and a sinusoid in velocity, which will then correspond to what we just looked at. This just looks like e to the I over h bar times the cosine of the initial position as our initial wave function, which we then let evolve according to the Schrodinger equation. We can now compare the densities of these 2 systems. The blue line shows the density of the wave function, while the red line shows the Zel'dovich case as before. Before shell crossing, these 2 look very similar, but at shell crossing, notice that our wave function doesn't go off to infinity anymore. After shell crossing, the interior region of our wave function develops rapid oscillations. We also no longer have infinite densities after shell crossing. These caustics have become smoothed by the waviness of our wave function. As before, we will show this information on a 2D space-time diagram. Here, we show the value of the wave function with the brightness corresponding to its amplitude and the color to its phase. Compared to what we saw in the classical case, we notice a few new features. Firstly, the caustic is no longer infinitely dense, nor is it infinitely thin. It's been regularized by an amount associated with the size of our parameter h bar. Secondly, we have this small-scale interference in the central region, which must correspond to classical multi-streaming. These are the main questions we want to examine. How can we unweave this wave function to see the classical streams? And how is other multi-streaming information encoded into the interference of the wave function? So we demonstrate that you can recover a set of wave functions, each of which corresponds to a classical stream from this interference. We see here that the wave functions represent this sort of behavior with a single wave function outside the classical cusp And then inside the cusp, we have one corresponding to particles flowing to the right, one to the left, and one straight down. This is precisely what we expect from the classical phase space sheet. If you imagine cutting the top, middle, and bottom layers of the twisted part. Crucially, however, we managed to do this unweaving just in space-time without having to construct a phase space for the wave function and manually dissect it. We can now look at how this decomposition works when we add all of these streams together. On the right-hand side of this panel, we show the full numerical evolution of the wave function, whereas on the right, we show the sum of the three wave functions that we just looked at. And you can see that this works really well, except for a very narrow region just around the caustic line. So now let's talk about how we actually do this unweaving. This unweaving is based on a propagator formalism, where we write the final wave function at a position x at time a as an integral over the initial wave function. We can bundle all of the things in the integral together into a single exponential, which depends on a function zeta. This function zeta contains the action and the initial conditions of our wave function. The key thing to note is that the integrand is highly oscillatory because h bar is a small parameter. This means that the terms in the integral will mostly cancel out with each other. This leads us to the stationary phase approximation, which says how we can unweave this interference. This approximation says that the integral is dominated by the points q, where zeta is stationary with respect to q. You can then calculate the contribution from each of these stationary points and add them up, as we did in the previous case. So each of these three individual wave functions that we looked at before corresponds to a different stationary point inside the cusp. Another way of thinking about this stationary phase approximation is the statement that the quantum propagator is dominated by contributions from the classical paths from initial positions to final positions. Now that we have this unweaving, let's look at how other information is encoded in the wave function. I said earlier that the velocity associated with the wave function is the gradient of the phase of the wave function. This looks like it means that the wave function can only encode potential velocities, like one would have with a perfect fluid. In the classical multi-streaming region, you have different fluid streams flowing through each other, which means that the velocity cannot be simply potential, right? Because we can't describe this as a simple perfect fluid. So if our wave function could only encode potential velocities, this wouldn't really be a step forward. So is our wave model doomed? Fortunately, no, there is a way out. If the phase of the wave function is discontinuous, then the gradient of the phase becomes ill-defined, and we could develop non-potential velocity points. We also know that where the density of the wave function vanishes, the phase is undefined. So maybe those are the points where this discontinuity could occur. Let's look at the phase of the wave function at a constant time. Let's take a slice through our 2D wave function, and indeed we see that the phase does develop discontinuities. And those discontinuities correspond to zeros in the density field. This means that our wave function can encode information beyond just a perfect fluid, and that that's stored in these phase jumps and density zeros, which are caused by the interference. This is good news because it means that our wave function allows us to encode information from this multi-streaming region in a way that a simple fluid model cannot. What does it mean to have a non-potential velocity? Well, in our one-dimensional case, this means that we have a non-trivial velocity dispersion, where multiple fluid streams differ from the average velocity in the central region. But if you were using a wave function model in 2 or 3 dimensions, you would see that these sites of zero density correspond to vorticity in the wave function. We can now look at how this velocity dispersion happens in our one-dimensional system, which we show on the right here. And we see on the left-hand side of this figure, the velocity dispersion. And on the right-hand figure, we compare where that velocity dispersion is to these pluses, which correspond to where the phase jumps are in our wave function. And you can see that the places that source velocity dispersion are in fact these phase jumps. Even better than that, using our wave decomposition, we can actually separate our full wave function into 2 parts. We have an average part that corresponds to the sort of bulk fluid velocity. So this would give us a mean density and a mean velocity. And then there's also this oscillatory hidden part of our wave function. And it's actually this hidden part of the wave function which sources the non-potential velocity, which in our case is a velocity dispersion, and all the other cumulants that you would expect. So to summarize, the stationary phase decomposition presented here lets us recover classical-like wave functions without having to construct a quantum phase space. We've seen that the interference of the wave model corresponds to multi-streaming stored in the phase jumps and the density zeros. We've also seen that a wave model of dark matter is very efficient at encoding this information, where we can encode information beyond a perfect fluid without having to go all the way to understanding the phase space dynamics directly. In addition to the classical streaming behavior, we can also examine the caustic itself. The unweaving of dark matter interference into classical trajectories, as we've discussed, is mathematically extremely similar to resolving wave optics into classical light rays. Fortunately for us, caustics in optics, like those formed at the bottom of a coffee mug, have been well studied and classified, and so we can leverage some of the mathematical techniques in optics into our case. Stable caustics have been fully mathematically classified into just a few forms. This essentially means a set of standard functions zeta, which would go into the wave function integral from before. While these standard functions zeta don't correspond to the initial conditions we've been using, the power of this mathematics is in classifying universal features for different caustic types. So we can relate these standard forms to the initial conditions that we were using by a set of coordinate transforms. And in particular, there are certain features that are universal for particular caustic types, like the maximum amplitude and the fringe spacing in different directions, which scale as different powers of h bar for different types of caustics. So to wrap up briefly, wave dark matter presents a rich phenomenology which decorates the cosmic web in interference phenomena, where we've seen that multi-streaming in the classical case corresponds to interference, and non-potential and beyond perfect fluid information gets stored in the phase jumps and their associated zeros. We've also talked about how wave models of cold dark matter efficiently capture information beyond perfect fluid models, which present exciting prospects for both analytic modeling and numerical techniques. Thank you very much for listening, and I look forward to chatting to many of you during the conference.